Okay, let's dive into this explainer and completely demystify the complex world of user identity and access in modern web applications. If you've ever wondered what's actually happening under the hood when you hit that login button, or how servers really keep your personal data safe from the bad guys, well, you are exactly in the right place. We're going to break down the technical mechanics of digital trust and see exactly how the whole shebang is built right from the ground up. So, here is our roadmap for today. We've got 6 key areas. First, the evolution of trust, then the core authentication building blocks. After that, choosing your auth strategy, OAuth and OpenID Connect, role-based access control, and finally, defending against auth attacks. All right, let's jump right into section 1, the evolution of trust, from wax seals to digital security. Okay, before we get into the technical weeds, we absolutely have to set a strict baseline here. Basically, authentication proves your identity, while authorization dictates your specific permissions within a system. To put it super simply, authentication answers the question, who are you in any given context? Like, are you really who you say you are? Authorization then answers, what can you do? Once we know who you are, what capabilities do you actually have? Can you just read a file, or can you completely delete it? These are the 2 fundamental pillars of literally every security flow we're unpacking today. Think about it. Scaling populations necessitated a massive shift in how we prove who we are. Back in pre-industrial societies, trust was kind of implicit, right? A village elder just vouched for you. But as society scaled, that implicit trust failed. We needed explicit proof. So we went from medieval wax seals, which were basically early physical authentication tokens, to the 1960s when MIT researchers introduced plain text passwords for mainframes, and those quickly evolved into secure, hashed storage. By the 1990s, the internet brought us multi-factor authentication, combining something you know, something you have, and something you are. It's really just been this constant race to stay ahead of the curve. Moving right along to section 2, core authentication building blocks. We're talking sessions, JWTs, and cookies. So, because HTTP is stateless by design, it inherently has zero memory. Imagine having to log in every single time you clicked a new link on a website, or losing your entire shopping cart just by hitting refresh. Nightmare, right? To fix this, sessions were invented to give servers a temporary memory of an authenticated user's actions. When the web became dynamic, servers essentially had to artificially create state. They do this by generating a unique session ID, storing your user data alongside that ID in a super fast persistent store like Redis, and then sending the ID back to your browser as a cookie to be automatically included in every subsequent request. But as applications grew globally, looking up a session ID in a database for millions of concurrent users caused some massive latency. Developers desperately needed a way to offload state from the server entirely. Enter the JSON Web Token, or JWT. A JWT packs everything needed for stateless verification into 3 distinct base64 encoded parts. You've got the header for metadata, the payload containing your user ID and claims, like exactly when the token was issued, and the signature, which is created with a secret key to make sure the token hasn't been tampered with in transit. It's entirely self-contained. That means the server can mathematically verify it without ever checking a database. A real game changer. Which brings us to section 3, choosing your auth strategy. Let's compare stateful and stateless architectures. Now, when you compare these 2 side by side, it really boils down to absolute control versus infinite scale. Stateful gives you that absolute control, but at the cost of server memory. If a user's account gets hacked, boom, the server just deletes the session ID from Redis and the attacker is instantly locked out. Stateless JWTs, on the other hand, scale infinitely because the server doesn't store a thing. The token is mathematically valid until it naturally expires. But if a hacker gets a hold of it, you can't easily revoke it without changing the master secret key. And doing that, unfortunately, logs out every single user on your entire platform. So yeah, it's a massive architectural decision. But wait, what if you don't have a human logging in via UI at all? Well, that's where API keys come in. They act as the perfect secure bridge for programmatic machine-to-machine communication. Think about it. Standard logins require a human to type a password or click a button. But what if your backend server needs to automatically ask the ChatGPT servers to summarize a paragraph? There's no UI for a human to interact with. Instead, you generate a cryptographically random API key, store it securely in your backend, and your machine uses it to seamlessly authenticate with another machine totally in the background. All right, let's jump to section 4, OAuth and OpenID Connect. This is how we solved the internet's delegation problem. Before OAuth, if a new travel app wanted to scan your emails for flight tickets, you had to hand over your actual raw email password. I mean, that is literally the equivalent of giving away the master key to your entire house just so someone can check your mailbox. It sounds completely insane today, but this was known as the delegation problem. That travel app didn't just get access to your flight tickets, they got access to the whole shebang, your photos, private messages, contacts, and you couldn't revoke their access without completely resetting your password across all your devices. It was an absolute security disaster just waiting to happen. So, to fix this absolute chaos, the industry created the OAuth 2.0 and OpenID Connect flow. Instead of raw passwords, servers now securely pass around specific VIP access tokens. Here's how it flows today. The client app redirects you to an authorization server, let's say Google. You log in directly with Google and grant permissions specifically just to read your emails. Google then sends a temporary code back to the client app. Finally, the client app exchanges that code behind the scenes for an access token. It completely transformed password-sharing chaos into the highly restricted, interconnected, and secure web we use today. Moving into Section 5, Role-Based Access Control, or getting granular with permissions. Now that we firmly know who the user is, we have to define exactly what they're allowed to touch. By mapping permissions to roles rather than individual users, backend engineers can securely gatekeep sensitive endpoints. Take an admin-only dead zone in a Notes app, for example. If you delete a note, maybe it doesn't delete permanently. It goes to a hidden dead zone database table for 30 days. You obviously only want administrators to access that data. So instead of checking permissions for every single individual user, role-based access control assigns roles upon sign-up. When a user makes an API request, the server immediately checks their role. If a basic user tries to access that dead zone, nope, the server instantly rejects it with a 403 forbidden error. And finally, Section 6, Defending Against Auth Attacks. Let's look at some real-world security best practices. Security rule number 1. Seriously, stop being so helpful. Never ever tell a user password incorrect or user not found. Why? Because that exact helpfulness gives malicious bots the exact clues they need to verify valid email addresses. While it feels like a great user experience to point out exactly what a person typed wrong, you are literally handing attackers a map. If you say user not found, the attacker knows to just move on to the next email. If you say password incorrect, well, now they know the email is valid, and they'll unleash dictionary attacks against that specific account. You gotta keep it perfectly vague. Just say authentication failed. Here's another hidden vulnerability you've gotta watch out for: timing attacks. Hackers can actually measure microsecond server delays to map out valid usernames, unless you simulate artificial, constant time responses. Think about it. If a username doesn't exist, the server drops the request almost instantly. But if the username does exist, the server proceeds to the next step, mathematically hashing the password, which takes just slightly longer. Hackers literally measure those tiny delays to harvest valid accounts at scale. You absolutely have to use constant time operations or simulate a fake server delay, so every single response takes the exact same amount of time. So, let me leave you with this. Is your current authentication system ready to withstand the post-quantum era? As quantum computers threaten to break modern asymmetric cryptography, evaluating your architecture today is the only way to secure the trust of tomorrow. The encryption currently protecting our JWTs and passwords relies on complex math puzzles that current hardware simply can't solve. But quantum computers? Eventually, they will. Understanding these foundational blocks of authentication and authorization now isn't just about building better apps today, it's about preparing your infrastructure for the massive cryptographic shifts heading our way. So, what's your next move to keep your system secure? Keep learning and keep building securely.